In 2022, scientists using a powerful telescope called the Murchison Wide Field Array stumbled upon an extraordinary discovery: a peculiar radio signal reaching Earth every 22 minutes. Such signals aren't entirely new to astronomers. They often originate from pulsars, rapidly spinning neutron stars emitting beams of light across space. Yet, upon delving into past observations, they found something remarkable. This signal had been consistently arriving since at least 1988, defying expectations with its unwavering regularity. If it originated from a neutron star, it behaved unlike any known before. The mystery deepened. What was the source of this enigmatic signal? To know more, stay with us till the end of the video. The place where the signal comes from, called GPMJ 183910, is super far away, about 18,000 light-years. Its signals come in pulses, lasting from 30 seconds to 5 minutes. These pulses pop up randomly within a bit more than 6.5 minutes, centered around 22 minutes after the last one. To us, this seems like a big range, but when it comes to neutron stars like this one, things get complex. Lots of stuff can mess with how long the pulses are and when they arrive. Still, astronomers managed to catch this signal in data from the past 35 years. They sifted through all the ups and downs to find an average. Turns out, the source spins once every 21 minutes and 58 seconds, and it's not really slowing down as expected. Even though it's radiating energy, the spin isn't changing much. If it had slowed down more than 0.28 milliseconds over 35 years, we would have noticed. But it's spinning super steady, which is pretty normal for a pulsar. These are the universe's timekeepers, ticking away consistently like cosmic clocks. They're known as pulsars, and one of them is spinning slower than usual. To grasp why this is strange, let's revisit what pulsars are and why they gradually slow down. Pulsars are the remnants of massive stars, incredibly dense neutron cores left behind after a star explodes. Imagine a star without its usual atoms, just a core made of densely packed neutrons. Even a small amount of this material weighs a lot, much more than all the people on Earth combined. A typical neutron star is much heavier than our Sun, compressed into a tiny sphere. These stars have intense magnetic fields, but why they do is still a mystery to scientists. How does this relate to the signals we receive from pulsars? Where does the light come from? To understand, we must delve into a complex process where light and matter burst forth from a single electron near the magnetic poles of the neutron star, kicking off what we call a pulse. The journey of a photon starts with a straight path, but things get interesting when it encounters a magnetic field. As the angle between the photon's direction and the magnetic field increases, it changes course. When this angle hits a certain point, the photon releases its energy into the electron field, creating an electron and its counterpart, a positron. These new particles gain some momentum at right angles to the magnetic field and emit synchrotron photons to get rid of it. These synchrotron photons can trigger the creation of more electron-positron pairs, repeating the process and rapidly multiplying photons and pairs. Eventually, the photons lose their energy, halting the cascade. They then shoot out into space, while the original electron keeps producing more photons, continuing the cycle along magnetic field lines. This cascade effect is why the light from a pulsar, even though distant, is so strong that we can pick it up from thousands of light-years away. Now, why does this pulsar light flicker instead of shining steadily? Well, it's because of the way neutron stars are built. Their magnetic poles don't line up neatly with their spinning axis, similar to how Earth's magnetic north differs from its geographic north. So, imagine pulsars as huge cosmic lighthouses, beaming light into space as they rotate. From our vantage point on Earth, it looks like the beams sweep past us repeatedly as the pulsar spins on its axis. This explains why we see the light from pulsars pulsating rather than shining continuously. These are the bursts of light our telescopes can spot. But it's a special kind of light, with long waves in the radio part of the spectrum only visible to radio telescopes. The light from the cascade matches this wavelength, with its waves rising and falling together. They're also polarized, lined up in the same direction. This alignment is a key sign of neutron stars, just like what we see in our 22-minute signal. There are also quick changes in the light's polarization, lasting from 0.2 to 4 seconds, where it shifts by 90 degrees and then back. This change is another clue of the cascades near pulsar's poles. The investigation into the 22-minute signal's origin initially pointed to pulsars, but challenges arose due to the slow spin of the emitting neutron star falling below pulsar Death Valley thresholds. Consideration then turned to magnetars, known for intense magnetic fields and occasional starquakes. However, the absence of expected X-ray emissions and the signal's unusually long duration of 35 years conflicted with typical magnetar behavior. This unresolved mystery highlights the complexity of celestial phenomena and the evolving nature of our understanding, emphasizing the ongoing quest to decipher the secrets of neutron stars and their enigmatic emissions. But what else could this mysterious signal be? The astronomers who found it suggested a few possibilities. One is a highly magnetic white dwarf. White dwarfs are leftovers from stars that died recently, but didn't have enough mass to turn into neutron stars. If a white dwarf has a really strong magnetic field, it could make radio waves. And since it's not a neutron star, it could spin slowly and steadily, like the source of GPM J183910. The problem is, it'd need an extremely strong magnetic field, stronger than any we've seen on a white dwarf. AR Scorpii is the only known radio pulsar that's also a white dwarf, but its radio waves are much fainter than our 22-minute signal. So, if a white dwarf is unlikely, what else could it be? Astronomers have seen low-frequency radio waves from stars interacting with exoplanets and from a pair of brown dwarfs orbiting each other. But these emissions are usually much weaker, about 100 million times fainter than our signal. In the end, none of our ideas seem to explain the 22-minute signal. Even though not knowing where the signal comes from might be frustrating, it's the kind of mystery astrophysicists love. When scientists discover new information that challenges what we thought we knew, it can change our understanding of the universe. Right now, what we thought about neutron stars is being questioned. The astronomers are pretty confident that if they found this signal easily, there are probably more out there in space, waiting to be found. Just like GPM J183910, there might be other signals hidden in the data we've collected. Finding more of these signals will help us understand how things emit light even when they're not typical neutron stars. Whatever is causing the 22-minute signal, it's going to teach us something brand new. Isn't that thrilling? What do you think might be making the 22-minute signal? Let us know in the comments down below. Like the video if you found our video interesting and share it with your fellow space enthusiasts. Subscribe to our channel for more content on space science. Hit that bell icon to never miss an update from us.